Okay, well, I'm gonna get started with announcements. They haven't really changed. The first assignment, getting started with WebAssign, is due on Friday. On WebAssign, it should be easy, because it is literally like, this is how you answer this type of question. It tells you what the answer is. The actual first assignment that's actual work is the chapter 1 homework. It's due Friday the 12th on WebAssign. And your first quiz on chapter 1 will be on the 10th, Wednesday the 10th in SI. So next week, Wednesday, will be your quiz on chapter 1 in the SI. Next week, Monday, we will have a lab, our first lab. Any questions about any of that? Everybody got on WebAssign, no problem? Okay. Come on. What does this always happen? So there's a few slides I managed to accidentally miss Wednesday last week because I opened the slides from last semester and they were off by a few slides. So I'll quickly go over these. So when we were talking about types of variables and communicating results, and one of the ways we can display results is in graphs, in line graphs. Generally, you plot the independent variable on the horizontal or x-axis and the dependent variable on the vertical or y-axis. And circle or pie graphs will show a fixed quantity using slices representing portions of the whole. So, each of these slices tells you how much of Texas weather deaths were caused by flooding, tornadoes, lightning, etc. So it's the pie graphs are there to show you the proportion of the whole. And then you can also use bar graphs to represent quantitative data in categories using bars. So the height of the bar tells you how much there is, and then each bar is labeled with the category. And so here, these bar graphs are set up to compare the values for each type of weather fatality for 2013, the 10-year average from 2004 to 2013, and the 30-year average from 1984 to 2013. So that gives you by looking at the longer term averages, you get an idea of how, whether this year is an outlier, the red, and whether there's been a trend in the averages, you can also see. So let's get back to where we were. Sorry about that mix up. I opened the wrong file, but they were basically identical, so I didn't notice. So accuracy and precision of measurements. So when we talk about measurements, all measurements have both an accuracy and a precision. And the easiest way to think about the difference between accuracy and precision is to think about shooting a target. So accuracy is the magnitude of agreement between experimental and accepted values measured through percent error. And precision is the magnitude of agreement between several measurements taken in the same manner, measured through significant figures. So precision is sort of the scatter, and accuracy is the aim. And significant figures include all the digits in a measurement known with certainty, plus the last digit in the measurement is estimated. So if you have a bullseye, so here, if you had an accurate measurement that was not precise, the grouping is centered around the bullseye, but it's very wide. So this is accurate, not precise. You could have a precise measurement that was not accurate. So this, you've got your setup. You have a very controlled setup, so you're always going to be hitting the same spot. But that spot is not where you want it. The spot is not the bullseye. So that would look something like this. This is precise, not accurate. And your ideal case is this is accurate and precise. Nice tight grouping in the bullseye. And the last possibility is you're terrible at both. You've got a big spread and you're off center. So this is not and not precise. So accuracy is measured by percent error. And it turns out like different sources of error cause different issues. So why is this stuck? If your error is being caused by like your machine being calibrated wrong, so it's got its zero in the wrong place kind of thing. Then you'll have reasonably precise measurements, but they won't be accurate. They'll all be off by the same amount. But if your error is being caused by your machine being cruddy, then you have in that, it's just not very precise. It wobbles around a lot. It has a lot of variation. Then your error will be accurate, but not precise. So here we have two measurements, and we want to look at which one displays greater accuracy. That will be done with looking at percent error. So percent error is you take the difference between the experimental value and the accepted value. You subtract the accepted value from the experimental value. You divide by the accepted value and multiply by 100 to turn it into a percent. So for example, if you weighed a rock sample you know should be 500 grams, and you got 499 grams, your error is going to be minus 0.2%. Because 499 grams minus 500 grams is -1. Divided by 500 gives you 0.2. However, if you weighed something that you know should be 2 grams and you got 1 gram, that we'd have an error of 1 gram minus 2 grams minus 1 gram divided by 2 grams and times 100, that would be -50%. So some constant error has a much bigger effect for smaller measurements. So this second measurement would be much less accurate, while this one would be more accurate. Now we can talk about precision. These are two measurements that have the same magnitude. They're both 2 grams. But we know that this is 2 grams to much more precision. That's why there's all these extra zeros here. They're letting us know that we know that this is only, plus or minus 1, 2, 3, 4, 5, 6, 7, 8, 9. Plus or minus 10 to the minus 10 grams. So like plus or minus 1/10 of a nanogram. While this one, you're really probably dealing with maybe plus or minus 1 gram. Then So this is much more precise than this. In fact, this is ridiculously precise. But so the way we express the precision of a measurement is in significant figures. So significant figures are a method of expressing measured numbers to their correct level of precision. Any mathematical operation like multiplication, division, addition, or subtraction can't give you more significant figures than you started with. So for example, 6.8 has 2 significant figures. 1.67 has 3 significant figures. You can count them. 1, 2, 1, 2, 3. So if you multiply these two together, 6.8 times 1.67 mathematically is exactly 11.356. But as a measurement, I don't know that I had this knowledge to this level of precision. So I will have to round this off to the same number of significant figures as the least precise input I have, the 6.8. So I'll round this off to 2 significant figures and get 11. And that's much more important when you divide than when you multiply, because division is likely to give you lots and lots of digits on your calculator. Your calculator is just going to give you as many digits as it can. So when you use a calculator and you do 6.8 divided by 1.67, you'll get something like 4.0718563, as you can see here. But not all these digits, not all these numbers are significant. Again, we're limited by our least precise input, which is 6.8. So that will need to round this to 4.1. And we round to 4.1 because we have 2 digits. We look at the next digit, it's 5 or greater, so we round up to 4.1. Because it is close, because this number here is closer to 4.1 than to 4.0. That's all you're doing when you round. So the general rule is you report only as many significant figures in the result as there are in the quantity with the least significant figures. And when multiplying and dividing, you express the answer to the same number of significant figures as the measurement with the least number of significant figures. So here, 6.8 centimeters divided by 1.67 centimeters, you round off 4.0718563 to 4.1. The limiting term is 6.8 with 2 significant figures. Now, when adding and subtracting, on tests and quizzes, I will accept doing it to the given number of significant figures. But the strict rule is for adding and subtracting strictly, you should be using decimal places and not significant figures. So here with 5.687 plus 11.11, you get 16.797. This has 2 decimal places, so you would round it to 1680. But you'll notice that if you did it to the correct number of significant figures, which would be 4, because both of these have 4 significant figures, you'd get the same answer. So usually, decimal places and significant figures will give you the same answer. Sometimes they don't. But I will accept both, because I'm not going to be super picky in this class. But you do need to round. So I would have marked it wrong if you put 1678. Well, I would have penalized you if you put 16797. By general policies, there's a penalty for the wrong number of significant figures. Not gonna lie. Completely marked. You're not gonna get no points, you're gonna get some points. Unless the question is something like write the answer with the right number of significant figures, then that's gonna be a bigger penalty. So why do we care about significant figures? Significant figures let us know how well we know the things we calculate. So they transmit information. And so it's important that you don't transmit false information. You don't lie with them, basically. So if you have a rock sample's mass was determined in the field to be 45.666300 grams using a ridiculously precise balance that measures down to the microgram. And then when brought into the lab, the volume was determined through water displacement to be 6.5 milliliters. And so the density was determined to be 45.666300 grams divided by 6.5 milliliters, which is 7.025584615 grams per milliliter. And the question you might ask, is it okay if I put this down as my result? And the answer is no, because this implies that we know the density of this material to this level of detail, to this level of precision, which we don't because our volume measurement was garbage. Well, wasn't very precise compared to our mass measurement. Our mass measurement was super accurate, but our volume measurement was way, way poorer. So our volume measurement is our limiting factor, because our volume measurement might be off by plus or minus 0.1 milliliters. And that's going to make a change in this around these digits, something around here. So all this stuff beyond that point is meaningless. So we need to round this answer to the same number of significant figures as the smallest value in the input. And that means 6.5 has 2 significant figures, so this should be rounded to 2 significant figures, which will give you 7.0 grams per milliliter. So 2 significant figures in 6.5, so you write this out as 7.0 grams per milliliter. Now let's go over how you identify how many significant figures a number has when you see it. So the rules for significant figures. All non-zero digits are significant. So 23.4 and 234 both have 3 significant figures. Same as 2.34. Any zeros in the middle, captive zeros, are also significant. They matter. So 20.05 has 4 significant figures. 1, 2, 3, 4. 407 has 3 significant figures. 1, 2, 3. Now, zeros on the front, leading zeros, never significant. Because the only purpose of leading zeros is to just tell you where the decimal point is. So 0.000035 only has 2 significant figures. Because again, zeros on the front never count. Now, trailing zeros generally only count when there is a decimal point. So if there's no decimal point, like 4,500, that would have 2 significant figures. So 45, but the trailing zeros with no decimal point don't count. But 45.0, that extra zero there is to let you know that that measurement was more precise. That has 3 significant figures. And sometimes when I want to use a nice round number on a test or a quiz, but I wanted to have more significant figures, I'll do something like write 300 and put a decimal point at the end and tell you that those zeros count. So usually when you're measuring, that's not so much an issue, but it comes up when you're writing tests because you want to use relatively nice numbers. And one way to make sure that you're always using, another way is if you write anything in scientific notation, all the digits in the, I guess it's called the mantissa, the front, the small number part that you multiply by a power of 10, those are always all significant. So the other way you can express a number if you want to make sure it's clear how many digits are significant is you can always write it in scientific notation. Because in scientific notation, so I could have written this as 3.00 times 10 to the 2, and all 3 of these would be significant. Because there's a decimal point, so the trailing zeros count. I should clear these. In fact, let me do that, and I'll go over these real quick. So let's go over how many significant figures are in the following measurements. 200.0 grams. How many significant figures do you think that has? It's 4. So there is a decimal point, so trailing zeros count, and all non-zero digits count. So 1, 2, 3, 4. So all 4 of the digits there are significant. This is 4, 6. How about 0.00458 grams? That is 3, yes. Leading zeros never count. 1, 2, 3. This is 3. How about 0.00400 grams? That's correct. It's also 3. Leading zeros don't count, but there is a decimal point, so the trailing zeros do. 505 grams. Yep, this is also 3. And lastly, 5 cupcakes. What do you think the number of significant figures there is? That is a reasonable assumption. If it was just 5, if it was 5 inches, that would be correct. However, in this case, this is an exact count of something. You can't have, when you're talking about 5 cupcakes, you have 5 cupcakes. You don't have like portions of cupcakes. You just have 5 things. In that case, if you have an exact count of something, like 5 cupcakes here, that's a special case, and basically all it means is you don't have to worry about the significant figures. You can assume it has unlimited. So exact numbers, exact counts of people, items, etc. You assume they have an unlimited number of significant figures, and you don't consider them when rounding. You basically just get to ignore, not worry about them. So for example, if a typical cupcake has a mass of 85 grams, what's the mass in grams of 8 cupcakes? Well, the 8 cupcakes, that's an exact number. We don't need to think about the number of significant figures. So we'll multiply 8 cupcakes by 85 grams to figure out the mass. 8 times 85 gives us 680, and that has 2 significant figures, so we're good. If you had 9 cupcakes times 85, that would be 765, and we'd have to round that up to 707. So in the process of determining the allowed number of significant figures, we generally have to round off. So the rules for rounding: if the first digit to be dropped is less than 5, you leave the last digit kept alone. So here, we round 26.142 to 3 significant figures. 26.1, that's 3. When we look at the next digit, that's a 4. That's less than 5. We do nothing. We just drop that stuff. But if the first digit to be dropped is 5 or greater, we have to increase the preceding digit by 1. So 10.063, the next digit is a 6. That is 5 or greater. You round up to 10.1. And the idea is that, so if you have 20.53, that is closer to 20.5 than to 20.6. It's between 20.5 and 20.6. It gets rounded down if it's closer to 20.5. If it's 20.57, that's closer to 20.6. That will get rounded up. So that's all you're doing. You're choosing, so any number is going to be between 2 numbers with the right number of significant figures. You choose the one that it's closer to, and the rule for that is if the first digit to be dropped is less than 5, it's going to be closer to the lower one, so you leave it alone. If the first digit to be dropped is 5 or greater, it's going to be closer to the higher one, so you raise it up. That is all. Any questions about that? Okay. So let's go through some examples of rounding off numbers. This is a very odd case when you round off significant figures. So we have 0.0997. We want to round this to 2 significant figures. I sort of have it right up there, but I'm just going to go through it so you can see the process. So I have 0.0997. This is a very special case that will only happen when you have a string of 9s. So if I look at this, I want 2 significant figures. So I'll go from the front. These aren't significant. This is my first significant figure. This is my second significant figure. I'm going to divide right there. This is a 7. 7 is greater than 5, so I have to round up. So going 1 up from 9, well, that's 10. So we get a 0. And that carries a 1 to this one. So there's another 9, we get a 0. And that carries a 1 to this one. So we get a 1. But if we look at this has more than 2 significant figures. This has 3. 1, 2, 3. So we have to drop the last one. But that particular case where you round up and it adds an extra significant figure or adds an extra digit from carrying, that will only happen when you have a bunch of 9s in it. So it basically never happens. But this ends up finding the correct answer is 0.1. Here, a more reasonable situation, we have 5.0 times 3.56. That's 1780. If we round this off to the 2 significant figures from the 5.0, that rounds up to 1800. The remote control remote. Oh, I guess we hadn't covered something. So sometimes we're going to deal with really big or really small numbers. And when we do, it's often more convenient to use scientific notation. So our number system, every place corresponds to a power of 10. You have ones, tens, hundreds, thousands. Each of those are, ones is 10 to the 0, tens is 10 to the 1, hundreds is 10 to the 2, and so on. So it's often useful to write numbers as a small number times a power of 10. This lets you write a convenient short number without having to write all those extra zeros and express a very large or a very small number more conveniently. So a power of 10, any number that is larger than 1 will have a power of 10 with a positive exponent, and a number less than 1 will have a negative exponent. So a million, for example, notice how there's 6 zeros here. That's 10 times 10 times 10 times 10 times 10 times 10, or 10 to the 6th power. And 1 over a million is 1 over 10 to the 6th. That's 10 to the minus 6, because taking something to a negative power is the same as dividing by that thing to a positive power. And that is 0.00001. And that's, the 6th place. So converting things between scientific notation and regular notation is all about moving the decimal point. I'm going to clear all this out. I should have cleared this out. Sorry. So here are some examples. So if we want to express 247 in scientific notation, what you're going to do is you're going to move the decimal point until it is after the first non-zero digit. So here the decimal point starts here, and we're going to go 1, 2 places to the left. And that will give us 2.47, because in scientific notation, we always write a number with exactly one number before the decimal point, and then we write it out like that, times, well, I move 2 places to the left, so every time I move 1 to the left, I have to increase the power of 10 by 1. So that's 2.47 times 10 to the 2nd power. Starts out as 0. You can think of this as 247 times 10 to the 0. Because 10 to the 0 is just 1. So multiplying 10 to the 0 does nothing. Here we have 186,000. So here, decimal point starts here. We got 1, 2, 3, 4, 5 places to the left. So we write this as 1.86, all the significant digits, times 10 to the 5th. Because I moved 5 places to the left. Here, I'm going to go 1, 2, 3, 4, 5, 6 places to the left. So I have 4.705 times 10 to the 6th power. And you can see how this makes writing really big or really small numbers a lot more convenient. Because sometimes I need to say something like 93 million or something. I don't want to write out 93 followed by 6 zeros. But I can write 9.3 times 10 to the 7th. And that's a lot more compact. And if we want to talk about something like the mass of the Earth, that's something like 6 times 10 to the 24 kilograms. I don't want to write 24 zeros. So yeah, or you want to talk about really small things. Part of the issue is that if you write these numbers out with just numbers, all the zeros start to blur together, and it's hard to tell how many there are. We can also write smaller numbers. if we move the decimal place to the right, we decrease the power going into the negatives. So here we go 1, 2 steps to the right. We get 2.5 times 10 to the minus 2. Here we go 1, 2, 3, 4, 5 steps to the right. We get 4.08 times 10 to the minus 5. And here we go 1, 2, 3, 4, 5, 6, 7 steps to the right. This is 1.0 times 10 to the minus 7. And so, you know, if you want to deal with some large number, like say the speed of light is 3.0 times 10 to the 8th meters per second. And that's much more convenient than writing it out. So let's express the average distance from the sun, the Earth to the sun, of 93 million miles in scientific notation. Anyone? That is exactly right. This is 9.3 times 10 to the 7. Because we were 1, 2, 3, 4, 5, 6, 7 steps. And then this would be miles. Because units are important. Now, if I ask you to say something in scientific notation, it has to be in this form with only one number before the decimal point. But if I don't, and you're just doing calculations, if you were just asked, you know, if you'd somehow done something that gave you the answer 93 million miles, I would accept 9.3 times 10 to the 7th miles. You could write out 93 million miles, but also 93 times 10 to the 6th is the same number, so I'll accept it. It's only if I specifically ask you to write it in a certain form that I'm going to be picky about it. And then when you're doing math with things in scientific notation, so if you have 2 times 10 to the 5th divided by, let's make this 8 times 10 to the 5th divided by 4 times 10 to the 3rd. Just doing math. What you can do, you can divide these 8 times 4. That's going to be 2.0. And then 10 to the 5th divided by 10 to the 3rd. What you do is you subtract the 3 from the 5. So this will be 10 to the 5 minus 10 to the 3rd. This will be 10 to the 2. So you just do what you would normally do with the front part. And then remember, when you divide powers or multiply, when you multiply powers, you add them. When you divide powers, you subtract them. So this 2 here is 5 minus 3. And so also if you had like 4.8, 4.0 times 10 to the 7 times 5.0 times 10 to the 4, 4 times 5, that's 20. And then 10 to the 7 times 10 to the 4, 7 plus 4, that is 11. So this is 20 times 10 to the 11. But you'll notice this isn't in scientific notation. Decimal place is here. So if I want to get it back into scientific notation, I'd have to move the decimal place 1 to the left and increase the power by 1. So this would be 2.0 times 10 to the 12. Because 4 times 5 is 20, but we have to increase if we move the decimal place 1 to the left to get it back into scientific notation, we have to increase the power. Any questions? Nope. I guess I'll erase this and continue to the next slide. So general rules. The exponent of power of 10 gets increased by 1 for every place the decimal point is shifted to the left. So 3,600, 360,000. You need to move the decimal place 5 places to the left. So you increase it to 3.6 times 10 to the 5. And it is decreased by 1 for every place the decimal point is shifted to the right. So here we go 2 places to the right, and we get 6.94 times 10 to the minus 2. And you can use these same rules to undo scientific notation. So here we have 6.94 times 10 to the minus 2. If I want to write this like a regular number, well, in order to get rid of minus 2, I need to increase the decimal place, the power by 2. So I'll move the decimal place 1, 2 places to the left, and I got 0.0694 times 10 to the 0, which I can ignore. Because 10 to the 0 is just 1. Anything to the 0 power is 1. And additionally here, with 3.6 times 10 to the 5, I need to move the decimal place 1, 2, 3, 4, 5 places to the left to undo that 10 to the 5. Because I'm going to subtract for each time I move to the left. I mean to the right. Mornings. So I'll get 3, 6, 1, 2, 3, 4. So here, if we have 5.6256 times 0.0012, that gives us 0.67507. We need to round this to 2 significant figures. That rounds to 0.0068. And if we change it to scientific notation, we have to move 1, 2, 3 places to the right. So we get 6.8 times 10 to the minus 3. And a general like sanity check, am I doing this right for scientific notation? Big numbers have positive exponents, little numbers have negative exponents. So if you're supposed to have a little number and you got a positive exponent, you probably screwed up somewhere, or vice versa. Here's another example. If we have 0.0024 divided by 8.05, that will give us 0.002981. But 0.0024 only has 2 significant figures. We have to round this to 2 significant figures. So 0.002981 rounds to 0.00030. And then if we want to change that to scientific notation, we have to go 1, 2, 3, 4 places to the right, which gives us 3.0 times 10 to the minus 4. And this trailing 0 is significant. It counts. So let's go over a sort of general way of approaching problem solving. Block you first. Are there any questions about significant figures, scientific notation? Okay. And if you want to practice significant figures, this isn't homework, it's just a practice sheet you can use. I have copies of a worksheet on significant figures up here if you want to practice. It has a very good write-up of rules for significant figures on it. But you don't need to take them. They're actually for a different class, but I have access. So Some rules for problem solving. First and most important step, read the problem. Read everything in the problem and identify. The most important thing is you need to read the problem and figure out what they're asking you for and what you know. Those are the important things to sort of note down. So read the problem, identify the principle that applies to it, and write down the given quantities with their units. So write down what you know, write what you're being asked for. So if you write down what you know and what you're being asked for, you know everything you need to have in your equations or what you're trying to find. And that lets you figure out what equation you need relatively straightforward math. So you write down what you know and what you're being asked. Sometimes you'll have more information than you need, but in general, you should be able to figure it out there. And it's often very helpful to draw a picture, because then you can figure out what you should be looking for. Determine what's being asked for, write it down. Then check the units and make conversions if that's necessary. So sometimes your givens will be in the wrong units for using your equations or things like that. So you may, or the wrong units for your answer, you may need to do conversions. So often you'll need to convert to whatever the base units are, because that's what the equations are. So like if you have a distance given in kilometers, but you have a formula that uses meters, you'll need to convert kilometers to meters. Then we can survey the equations and figure out what the appropriate one. If you've written down what you know and what you're looking for, often the equation that you want will be the one that contains what you know and what you're looking for and nothing else. So, that can help you figure out what the right equation is. So, if the equations are used, you could possibly use are, velocity is initial velocity plus acceleration times time. Position is initial position plus initial velocity times time plus 1/2 acceleration times time squared, and initial velocity squared for the initial velocity squared is initial velocity squared plus 2 times acceleration times change in position. And you need to pick which of these equations to use, and you're given initial velocity, acceleration, and distance, and you're looking for final velocity. Well, you'll notice the thing you don't have any information on is time. So you'll want to use this equation that doesn't have time in it. It's actually possible to do this by using both of these, but it's much easier to use this equation. But that's just an example. I just pulled up some equations we're actually not going to use in this class. So less of an issue. But I'm teaching them in physics right now. So they're sort of on the top of my head. So you need to read the problem, identify the principle, figure out what you want. Then we can look at the equations, figure out the appropriate one, and do the math using appropriate units, and round off and adjust to the appropriate number of significant figures. So here's an example problem. The Earth goes around the sun in a nearly circular orbit. That is telling you we're dealing with circles. So we need equations about circles with a radius of 93 million miles. So things we know. We were just told the radius is 93 million miles.
And the question is, how many miles does Earth travel in making one revolution around the sun? So we want to figure out the distance for one complete circle. So this is asking us for circumference. So if we link back to our equations about circles, the appropriate equation about circles. So one revolution is once all the way around. We draw, if we draw a picture like this, okay, we have the radius, we know what that is. We're going to go around once. That is the circumference. The picture lets you can help figure out what it is exactly you're looking for. And so if we look at circles, the formula for circles, circumference is 2 pi times the radius. So we can plug in our numbers. So we know our radius is 93 times 10 to the 6 miles. That's 93 million miles. We are looking for the circumference. Circumference is 2 pi times the radius. So by determining which parts of the equation are, useful information, this tells us we're working with circles. This tells us the size of the circle because of the radius. And then this is asking, we're looking for miles traveled in one revolution around the sun. That is asking for circumference in miles. We're looking for a distance. How many miles does Earth travel in making one revolution about the sun? Well, one revolution about the sun is going around the circle once. So that is the circumference. And then we can attack the problem. We need an equation for a circular orbit, the circumference. We know the radius, that's 93 million miles, it's given. Our answer also needs to be in miles, so we don't have to do any unit conversion. That's nice. And so our equation is circumference is 2 pi times radius, where pi is 3.14159. In general, 3.14159 is a good enough approximation of pi for almost any purposes. But you can always use the pi button on your calculator, which will have more digits than that. But 5 decimal places is generally good enough for like almost anything. So now we can plug the numbers in. Our circumference is 2 pi times the radius. Pi is 3.14159. 2 times 3.14159 times 93 million miles gives us 58, which is 2 times 3.14159 times 9.3 times 10 to the 7 miles, which is 58.433574 times 10 to the 7 miles, which we could round off to 58 times 10 to the 7, because 93 million only has 2 significant figures. So we need to round our answer to 2 significant figures. So we round off to 58 times 10 to the 7, and then we move the decimal place 1 place to the left to put it in scientific notation. And we have 5.8 times 10 to the 8 miles, which is 580 million miles. And that's the distance the Earth travels in one revolution around the sun. Now, density is a measure of the amount of stuff in a substance. So I think we talked about this earlier. We mentioned density. Density is generally measured in grams per cubic centimeter. So let's do a problem about density. So the density of iron is 7.87 grams per cubic centimeter. Every cubic centimeter of iron has a mass of 7.87 grams. So let's determine the volume of a sample of iron that is 58.222 grams. So density is mass over volume. If we want to find volume, we're going to do a little algebra. We multiply both sides by volume. We get density times volume equals mass. And then we can divide by the density. Volume equals mass over density. So, knowing that volume is equal to mass over density, we can do 58.222 grams times, well, divided by 7.87 grams per cubic centimeter. And that will give us 7.397966963 centimeters cubed. But that has too many significant figures. So this should be rounded to 3 significant figures, I think, because of the density of iron. We only know it to 3 significant figures. So this will be 7.40 cubic centimeters. So rounded off properly, it will be 7.40 cubic centimeters. Because this is the limiting term with 3 significant figures. So remember, density is mass over volume. Your book does use rho, but I'll try and use a capital D just to make it clearer. And our first lab will be about density. So you should be familiar with this. So this is density. This is, we're looking for volume. We know mass. And this is how we get volume equals mass over density. So let's review chapter 1 and go through. So what branch of earth science involves the study of the atmosphere? That is meteorology. What branch of earth studies the structure of the earth? Yes, it is geology. What branch of earth science studies the planets, stars, and other things in outer space? Astronomy. Our senses allow us to make what about the world around us? No, observations. A possible explanation for the subject of number 4, that is a hypothesis. So our senses let us make observations, then we think about them and make a hypothesis about it. And what do we carry out to check if our hypothesis or our possible explanation is plausible? No, we do experiments. Theories are confirmed hypotheses. An accepted explanation for a phenomenon that stands up to testing is a theory. And a concise statement that only describes but does not explain phenomena, that is a law. So that's the difference between a theory and a law. A theory explains what's going on. A law just describes what's happening. So you might have something like the law of conservation of energy. But there's like a theory of symmetry that explains why energy is conserved. So which variable in an experiment is controlled by the experimenter? That is the independent variable. It's independent because you can set it to whatever you want. Okay. And then which variable is in an experiment is a change looked for? That's the dependent variable because it depends on the independent variable. What are the 3 common fundamental units, often measured in meters, kilograms, and seconds? What are the 3 things those are measured? These are length, mass, and time. That's a weirdly worded question. But the three fundamental quantities that are. The metric system is based on the number what? 10, yes. It's powers of 10. So what are the meanings of the following metric prefixes? What does kilo mean? Yes, but what's the number that it means? So how many meters are in a kilometer? It's 1,000. So kilo is 1,000. If you wanted 10, it would be deca. Centi. What is? No, centi is small. Centi is 100th. So a centimeter is 100th of a meter. Milli. What fraction of a meter is a millimeter? What fraction of a second is a millisecond? It's 1,000. So centi is 100th, milli is 1,000. They both come from the Latin terms for, 100th and 1,000. And mega is another big one. How many tons are in a megaton? Nope. More than that. Yes. Mega is a million. So above 1,000, they go every 1,000. But 10,000 doesn't have a special mass. So what do we call the mass per unit volume for a substance? That is density. And here I have the conversion of 18 feet to meters, given that there are 2.54 centimeters per 1 inch. So your first step is to go from feet to inches, 18 feet times 12 inches per foot, from inches to centimeters, 2.54 centimeters per inch. And then from centimeters to meters, 1 meter is 100 centimeters. So we divide by 100, and that will give us 5.5 meters. And if we want to convert 250 centimeters to meters, centimeters is 100th. So we're going to divide by 100 to go to meters. So 250 centimeters divided by 100 gives us 2.5 meters. Significant figures are used to express the level of precision in a measurement. The closeness of a measurement to its true value is an expression of its accuracy and can be measured by calculating a percent error. And then how many significant figures are in the measurement? 0.900800 centimeters. That is 6. And the answer to 34.60 times 22, well, that's 761.2, but 22 only has 2 significant figures, so we'll round it to 760. If we want to express the number 201,000 in scientific notation, it's 2.01 times 10 to the 5. The number of 0.00950 in scientific notation is 9.50 times 10 to the minus 3. If we have a rock with a mass of 6.50 grams that displaces 34.0 milliliters, then we want to calculate its density. 6.50 grams divided by 34.0 milliliters gives us 0.1911767 grams per milliliter, which we would round to 0.191 grams per milliliter. And then lastly, with mercury, the density of mercury is 13.6 grams per milliliter. So what would the mass of a 3.4 milliliter sample be in grams? We're going to take the density, multiply by the volume, and get the mass. which rounded off is 46.2 grams. That is it. Any questions? We're done for today. I'll see you next week. Remember, you have SI today. Have a nice weekend. And do remember to do that first homework, but it's easy. Have a good day.